Hello class, I wish you all had enjoyed the long weekend. And now let's go back to our lecture. So today we're going to talk about frequency distribution, histogram, and Pareto diagram. Now let's go back to the example about number of daily billing errors. So we have already examined the first two columns. The first column stands for class. It's just another word for the number of non-conforming units, or in this case, the number of daily billing errors. So the number of daily billing errors could take 0, 1, 2, 3, 4, or 5. And the second column, frequency, records the number of days that is having this number of daily billing errors. So we have a total of 52 days. Therefore, the total number of our data points is 52. And if you use the second column, divided by this total, divided by the 52, then we got this relative frequency. So relative frequency stands for the proportion or fraction of the total. For example, in this cell, it says 38% of days are having one daily billing error, and 15% of the days are having two daily billing errors. The fourth column is cumulative frequency. So cumulative frequency is the number of data points equal to or less than a data value. For example, this cell tells us there are a total of 43 days when the number of daily billing errors is less than or equal to 2. When you are computing a cumulative frequency for a class, for example, in this case for class 2, then you just need to sum up all the frequency up to class 2. So you sum up 15 plus 20 plus 8, and that gives us 43. You can also use the cumulative frequency of the last class and plus the frequency of the current class, so that you can get the cumulative frequency of the current class as well. The last column is relative cumulative frequency, which is calculated by the cumulative frequency divided by the total number of data points, 52. So for example, this cell tells us out of the 52 days, 83% of the days are having less than or equal to 2 daily billing errors. To double check our data, you can see that the relative frequency should sum up to 1, because they are just different portions of the days that is in different classes. And for the cumulative frequency, it must end up with the total number of data points in the last class. And the relative cumulative frequency must end up with 1 in the last class. The graphic representation of frequency distribution is a frequency histogram. So here is the frequency histogram for the daily billing errors example. And the horizontal axis stands for the classes, or the number of non-conforming units. Like we can have 0, 1, 2, 3, 4, or 5 daily billing errors. And the vertical axis stands for the frequency, aka the count of each class. So we can tell that there are 15 days without a billing error, and there are 20 days with one daily billing error. And we can see that these frequency shows some descending phenomenon relative to the number of non-conforming units. We can also draw the relative frequency histogram. This is similar to the frequency histogram, except the vertical axis now stands for the relative frequency, which is the proportion of the frequency compared to the total in each class. And if you go back to the frequency histogram, you can see that they share the same shape, except they are in different scale. So in this specific example, the relative frequency histogram is the frequency histogram divided by 52 in the vertical axis. So for relative frequency histogram, the range of the vertical axis cannot go over 1. It is always between 0 and 1 because it is a percentage. Now let's have a look at the cumulative frequency histogram. So the vertical axis stands for the cumulative frequency, and the value of these bars must be ascending from class to class. This is because of the way that we construct it. So for example, there are 43 days with less than or equal to 2 daily billing errors. And I want to know what is how many days are having less than or equal to 3 daily billing errors. Then I just need this 43 plus the 5 days that is having 3 daily billing errors, and then I'm going to have 48 days having less than or equal to 3 daily billing errors. Here is the relative cumulative frequency histogram. Again, it shares the same shape as the cumulative frequency histogram, just having a different scale here. Because this is the relative cumulative frequency, it must be between 0 and 1. Now we're going to talk about a fast way to construct a histogram. So this is especially useful for grouped data. If we have categorical frequency distribution, then we already know what the classes are look like. For example, the 12 months of the student's birth, right? Or if we have ungrouped data, then we can enumerate the classes. So the classes is just the enumeration, like number of girls in a 4-child family. So the classes are 0, 1, 2, 3, 4. The only tricky histogram to make is the histogram for grouped data. So you have a large range of data points. Therefore, you need to set the boundaries for each class. So the first step is to find the range of distribution, which equals to the largest value in your dataset minus the smallest value in your dataset. And step 2 is to choose the number of classes. We normally take 5 to 20 classes. Sometimes we use cells to replace the classes. They actually mean the same thing. So here are 3 rules to define the number of classes. If the number of observations, that is the number of data points, is less than 100, then we want to have 5 to 9 cells. If the number of observations is between 100 and 500, then we need 8 to 17 cells. If there are more than 500 data points, then we want 15 to 20 cells. So after you choose the number of cells or classes, then we can determine the width of the class. So the class width equals to the range divided by the number of classes. And from step 2 and 3, we can determine the boundaries for each class. And because we're going to draw the histogram, which has all those columns, so normally we didn't use the boundaries to define on the graph to represent each column. We used the midpoint of each class to stand for each column. So the midpoint is the average of the cell's two boundaries. And step 5 is to draw the frequency histogram. Here is an example of grouped data. So we have a total of 110 observations, and they ranges from 2.531 to 2.575. As you can see, the smallest value of our dataset is 2.31, and the largest value is 2.575, which occurs twice in our dataset. So here is a bunch of steel shaft weights from a production line. They need to abide by some specifications, but the actual measures of all these 110 products may vary a little bit from each other. Therefore, the range of our datasets is 2.575 minus 2.531 equals to 0.044. And if we go back to the previous slides, we have 110 observations, and therefore we need to have some number of cells between 8 and 17. So I pick 9. I choose the number of classes as 9, and therefore the class width equals to the 0.044 divided by 9, and that gives me a 0.005 of the class width. There are also some other types of frequency distribution graphs, like bar graph, polygon of data, cumulative frequency distribution, also named as algebra. On the left-hand side is a bar graph for the number of daily billing errors. So you just draw a bar for each class to the height of each frequency. So the bar graph is theoretically correct for discrete data. However, it is not suitable for grouped data. On the right-hand side is a polygon of the data for the steel shaft weights. So we make a dot for each midpoint of each class, and this dot has a height of the frequency, and then we use a line to link all these dots, and it forms a polygon. This dotted curve shows the cumulative frequency of the steel shaft weights. So it starts with the smallest weight, and then it's cumulatively growing up. At the largest weight, it reaches 110, the total number of data points, which is also the cumulative frequency at the last point. Next, we are going to talk about Pareto diagram. So Pareto diagram is introduced in our textbook in chapter 3, and I'm going to put it here because it's just a special case of histogram. So Pareto diagram rank the data classifications in descending order from left to right, and with others in the rightmost position. So others is just one class that is not specifically defined. So Pareto diagram is a sorted and categorical histogram. It is sorted because the classes needs to be in a descending order of their frequency, and it is categorical because each class must be a description of the problem of the quality or the reason of failure. So Pareto diagram is used to identify the most important problem of quality. So here's an example for paint nonconformities. As you can see, we have categories or the classes that stands for the different nonconformities, and we sort them or rank them by the descending order of the frequency of each problem. And therefore, we draw this histogram, this sorted histogram as a Pareto chart. And we can also draw this relative cumulative frequency distribution curve. I want to point out that the last class or category, others, just stands for all the other reasons or failure problems that was not presented in the previous categories. So this must be put on the rightmost position, even if this other may have some higher height, or aka larger frequency than some specified categories. These others should still be on the rightmost position. So today's assignment is to read section Frequency Distribution Chapter 4 and get an idea of the rigorous steps in constructing a histogram, which is on pages 128 to 130. That's all for today. Bye-bye.